After considering the Kolmogorov forward equation, it is time to look at the Kolmogorov backward equation and see what it does. Okay, so the Kolmogorov backward equation, or if you like, call it KBE. This lesson provides a systematic and comprehensive explanation of the Kolmogorov backward equation, including derivations, intuition, and worked examples. The objective is to understand how to compute u t comma x, which is equal to expected value of f of x comma t, given that x of t is equal to x, where x of t is a stochastic process, f is a terminal payoff function, and t is the final time. So the key idea is that the Kolmogorov backward equation describes how expected values evolve backward in time. So expected values are evolving backward in time with this. So instead of evolving probability forward, we evolve expectations backward. So the case of Kolmogorov forward equation was evolving probability forward, but in this case we evolve expectations backward. So 35.1, now we have the Markov process setup, which first we assume a diffusion process where the x sub t is equal to mu of xt comma t dt plus sigma x of t comma t d wt, and we define that u of t comma x is equal to expected value of f of x sub t, given that x of t equals x. And then we have the Kolmogorov backward equation. So the function u of t comma x satisfies partial u partial t plus mu x comma t partial u partial x plus half sigma squared x comma t partial squared u dx squared equals 0. And it has a terminal condition that u is t comma x equals f of x. Now, this looks way heavier than what we saw with the Kolmogorov forward equation, but let's go for it. So the intuition behind the equation is that we use the idea that u of t comma x is the expected value of u of t plus delta t comma x sub t plus delta t. Then we use the Taylor expansion. U of t plus delta t comma x of t plus delta t is approximately u plus u sub t delta t plus u sub x dx plus half uxx dx squared, and we substitute the x to be mu t plus sigma dw, and dw squared, we take that to be dt. So taking expectation, then we have that ut plus mu u sub x plus half sigma squared uxx is equal to 0 in that case. And then that leads us to the concept of the Brownian motion. If we consider that the x sub t is equal to the w sub t, then mu is equal, if you take mu to be 0 and sigma to be 1, okay, then the PD can then become, it's like from here now, mu is 0. So because mu is 0, this term goes, so we have ut left, then sigma squared is 1, so we have half uxx equals 0. We have that PD like that, and then we have the terminal condition now to be, I think we saw terminal condition somewhere before. The terminal condition now is u of t comma x is equal to x squared. Okay, yeah, it's f of x. So now we take it to be x squared in this situation. Then if we solve that, we compute x sub t equals x plus w big T minus w small t. Then we say that u sub t comma x is expected value of x sub t squared equals x squared plus t minus big T minus small t. And then we can actually, do the simulation using Python. And then that ends up just giving us 0 like that. Okay. So, and in example 2, we have the Brownian motion with drift. So, here, this is just the Brownian motion, no drift, right? But Brownian motion with drift, the drift term now is the mu delta t, mu dt term now, because previously we had d big X sub t plus d big W sub t. So the PD now is then u sub t plus mu sub x plus half mu xx equals 0, and the terminal condition is u of t comma x equals x. And then we solve this, we compute that to be x sub t equals x plus mu into t minus t plus big W sub t minus big W, big W sub big T minus big W sub small t. Thus, we have u into t minus t comma x equals expected value of x comma x sub t equals x plus mu t minus t. So if we simulate this also, we get that zero value right there. And we move to 3, where we have numerical solution for finite, that's finite difference as numerical solution. So here we solve that. We solve mu sub t plus half mu x equals 0 with terminal condition u into t comma x equals max of x comma 0. And then we have the discretization. For the time grid, we have t sub n. For the space grid, we have x sub I. And then we have finite difference approximation, which is mu u sub I n minus 1 equals u sub I n minus delta t dot half u sub I plus 1 power n minus 2I n, not power per se, it's just the level, the step level n plus ui minus 1 n over delta x squared. So talking about the time and space grid, and then we can simulate that using our Python code. We take nx to be 100 steps and nt to be another 100 steps for the parameters. The maximum value of x is 5 and the maximum time is 1, and then dx is 2x max over nx, and this is t over nt. So we do all that. By the time we simulate, we get some beautiful results like this. So for the backward solution, so we have this kind of behavior like this. Then, so talking about the connections now, how does this connect with the Kolmogorov forward equation? We see that forward equation involves probability density, while backward equation involves expectations. And then we have the Feynman CAC formula. The solution to the PD can be written as u rather, u t comma x equals expected value of f of x sub t. And then we have the Black-Scholes equation, a special case of the backward equation, which is u sub t plus rx, u sub x plus half sigma squared x squared u xx minus r equals 0. So in summary, we see that the Kolmogorov backward equation computes expected future values, and it evolves backward from terminal condition. It is derived using the Ito calculus, and it connects stochastic processes and partial differential equations. And the key formula is this, that the partial u partial t plus mu x comma t partial u partial x plus half sigma squared x comma t sigma squared of x comma t d squared u dx squared equals 0 with mu u t big T comma x equals f of x, like that. And then that brings us to the practice problem. Some we have seen already. So you want to try your hands on this to see how well you understand the concept as explained earlier. So we have more of theory and derivation problems here. So you want to look at this alongside what we did in the notes and try your hands on them. So let me know how helpful this is for you. And if there's something else you like me to try out, feel very free to let me know. So here you have question 1 to 3, then you have 4 to 8, then you have 9 to 12, then you have 13 to 16. You have 13 to 16. Then you have 17 to 20. So let me know how helpful it is and all that. Yeah, if you have subscribed already, thank you very much for doing that. If you haven't subscribed, why not go ahead and subscribe right now? Hit the notification bell also after subscribing so that you can always get alerted each time a new video is released. You can also click on join to become a member of the channel. That gives you special privileges like getting to see some videos first or seeing some videos exclusively because you're a member of the channel. We can also hang out to discuss whatever interests you on the channel. We can also, you can request for PDF copies of my notes, the notes I use in teaching some of these classes. Um, Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.